So Hess's law, another name for Hess's law is the law of constant heat of summation, which basically means summation adding up the enthalpies. Whatever we do to the manipulation in equation 1 and equation 2 or 3 or 4, whatever we need to do to explain the reaction that we want to try to measure the enthalpy on, in this case, reaction 1, okay, so ABC going to AB plus C. If we can't measure that directly, but we can measure reaction 2 directly and reaction 3 directly, then as I've shown here, we add up reaction 2 and 3 and we actually get reaction 1. Then we can take the enthalpy that we measured from reaction 2 and reaction 3 and add those up. That's what I showed on top, circled in green, okay? So they add up. It's a very, very useful relationship. So we're going to be playing around with that today. I'm going to lead you through an example, and then I'm going to maybe have you do one on your own, and I'll lead you through that. And let's just see how that goes. So here's the first example. Let's say that this is the reaction that we want to calculate the delta H for. But we can't measure it directly. But we do have all of this combustion data. Now, you remember combustion. That's where you take something and you mix it with molecular oxygen. And the products that you get out of it typically are carbon dioxide and H2O, depending on what it is you're combusting. In this case, in reaction 1, we're combusting carbon, so all we're going to make is carbon dioxide. In equation 2, we're combusting hydrogen gas, so all we're going to make is H2O. And in equation 3, we're combusting some methane, CH4, and we're getting our expected products, CO2 and H2O. All right, so these combustion reactions, they're all balanced. And on the right-hand side, I'm giving you what the delta H of those reactions are. Okay, so let's see, how can we manipulate 1, 2, and 3 such that if we manipulate them and then add them together, we'll actually describe the reaction in blue that we want to characterize. And it's somewhat of a logic puzzle, okay? The way you do these is, well, let's take a look at reaction 1. What is there in reaction 1 that we need in our final reaction? What do you see? Carbon, oxygen, or CO2? We need carbon, right? And carbon, so how does it exist in equation 1? It exists as a reactant, and there's 1 mole of it. And that's exactly what we have in the reaction we're trying to describe. 1 mole of carbon in the reactant side. So we don't need to manipulate reaction 1 at all. We can use it directly as it is, kind of like in the ABC example I showed you above. So the way I recommend you do that is put a little notation down here. Here's reaction 1, and let's just write it out the way that it is presented. And without manipulating it then, the delta H of this reaction is going to be equal to negative 393.5 kilojoules per mole. I haven't done anything. Okay, let's move to reaction 2. What's in reaction 2 that we need in our final reaction? Hydrogen gas. We've got 2 moles of hydrogen gas on the reactant side. What do we need in our final equation? We need 2 moles of hydrogen gas on the reactant side. So once again, we don't need to do any manipulation. We can use reaction 2 directly because it already has what we want in the right place and the right number of moles. So there's no manipulation here. So let's just take reaction 2 as it is, and let's write it down. 2H2 gas plus O2 gas will combust and give us 2 moles of H2O liquid. And the delta H for that reaction is equal to minus 571.6 kilojoules per mole. Now, I want to just mention here real quick, when you're working with H2O, sometimes it's in liquid and sometimes it's a gas, and it does make a difference. So you really do need to pay attention to the states of matter. Because as we've discovered, there is an enthalpy component to converting H2O from the liquid to the gas phase. So depending on what you're working with here with these numbers, it's going to make a difference what the enthalpy value is. Okay, but in this case, this enthalpy component, negative 571.6, that's for those reactants combusting, but now we're doing it for H2O liquid. And by the way, you can look all of these values up, or a lot of these values up. You'll be seeing soon enough in one of the appendices in your textbook. The appendices are very, very useful. And we're starting to use them a lot in this chapter. All right, so those are the first two. What about the third one? What do we have in the third one that we need in the reaction we're trying to describe? I heard it. Say it louder. CH4, the methane. Okay. Reaction 3, as it stands, has 1 mole of methane as a reactant. What do we need in our reaction? We need 1 mole of methane as a product. So what are we going to do to reaction 3? We're going to reverse it, okay? But we don't need to multiply it or divide it by anything, because we only need 1 mole of methane for our balanced equation up on top that we're trying to describe. So we're going to reverse it, all right? And the way that I like to notate that is just put a little negative sign in front of reaction 3. We're just reversing it. So let's write reaction 3 in reverse. That's going to be CO2 gas plus 2 H2O liquid. We'll go in reverse to give us 1 mole of CH4 gas and 2 moles of oxygen gas. I want everything lined up here. All right, so the delta H then for that reaction, because I reversed it, all right, here's delta H for the reaction as written, but I reversed it. So I'm going to reverse the sign on delta H, right? It's the same quantity, but remember the positive and negative sign just has to do with the flow of thermal energy. Well, in this case, if we run the reaction backwards, the energy is going to flow backwards. But we're not doing anything to the absolute value of that energy. So now delta H of this reaction is a positive 890.3 kilojoules per mole. Now, if we did this correctly, if the left-hand side all adds up to the reaction that we're trying to describe, then we can add up these enthalpies and we'll get the enthalpy of the reaction that we're trying to describe as well. So let's make sure this adds up. Let's see, we've got CO2, 1 mole of CO2 cancels with 1 mole of CO2. We have, we've got 2 moles of O2 that are going to cancel with 2 moles of O2 over here. Okay, do you see how I did that? All 3 of these are being added up. So we have 2 moles of oxygen gas on the left, and we have 2 moles of oxygen gas on the right in total. What else can we cancel out? H2O, yes, thank you. 2 H2O here and 2 H2O there. So that leaves us then with, hopefully, what we're trying to describe. Carbon, solid, 1 mole, plus 2 moles of H2 gas goes to give us, combines now to give us 1 mole of CH4 gas. Okay? So the delta H of this reaction then is going to be equal to whatever those add up to. 0.3, so I get negative 74.8 kilojoules per mole. That's the delta H for that reaction. Because the one that I wrote down in red is exactly the same one that we're trying to describe. All right, so now we can say, is that reaction endothermic or exothermic? It's exothermic because as written, it has a negative value for delta H. So this system is giving off energy when you have 1 mole of carbon combining with 2 moles of H2 to give us 1 mole of carbon dioxide, methane gas. Okay, so that's how it's done. That was one example. Now that you've seen me do it, we're gonna give you a chance to do it. But first, let's, so here's another combustion. We're combusting some ammonia with O2 to give us some nitrogen gas and H2O. But first we have to balance this equation. We've got 2 nitrogens over here. So we would put 2 over here. That gives us 6 hydrogens. So to give us 6 hydrogens, we would put a 3 over here. That gives us 3 oxygens on the right, but we only have 2 oxygens on the left. So we'll use our fraction, 3 halves. Now the oxygens are balanced. But in this molecular reaction, we can't have fractions. So we need to get rid of that. We'll multiply everything by 2. So that turns this into a 4. This stays as a 3. This becomes a 2. And this turns into a 6. Okay, so you want to give this a shot yourselves? I'll give you a couple minutes head start, okay? And then I'm going to jump in and lead the rest of you through it. 530 kilojoules per mole is the right answer. Right, but let's see how we got there, okay? Let's take you through it all. So look at reaction 1. I'm looking at that and I see we've got nitrogen, hydrogen gas, and ammonia gas. We've got nitrogen gas that we want as a product and ammonia gas that we want as a reactant, and we need 2 moles of one and 4 moles of the other. In reaction 1, we've got 1 mole of nitrogen gas as a reactant and 2 moles of ammonia gas as a product. So if I reverse reaction 1 and multiply it by 2, I should have what I need in the final reaction. So I'm going to notate that as I'm going to take reaction 1 and I'm going to reverse it, and I'm going to multiply it by 2. I'm going to do all of that in one step now. I'm going to translate that down. So that's going to be then starting with the 2NH3, but I need to multiply that by 2 and put it as a reactant. So I'm going to have 4NH3 gas is going to decompose into 2 moles of nitrogen gas plus 6 moles of H2 gas. Okay, everyone see how I did that? Now I need to do the same thing to the delta H. Whatever you do to the reaction, you do to the enthalpy. So now the delta H of this reaction, as written, okay, is going to be, let's see, positive 92.2 and then double. So that should be 184.4, right? See, I don't need a calculator. Plus 184.4 kilojoules per mole. And that's why I'm very particular about saying this is for the reaction as written. Notice that the delta H is different, even though the reaction is about the same, but we're manipulating it now. All right, how are we going to manipulate number 2? We need, what do we need? H2O and oxygen gas, but we don't need H2. But notice that both reactions have hydrogen gas, so hopefully it's going to cancel out. We need 3 moles of oxygen and 6 moles of H2O. We can get that by multiplying reaction 2 by a factor of 3, right? But we don't need to reverse it because we need H2O as a product. So let's just notate that as we're going to take reaction 2 and we're going to multiply it by 3. That's going to give us 6 H2 gas plus 3 O2 gas will combust and give us 6 moles of H2O liquid. So the delta H for this reaction has to be negative 571.6 times 3. So here, let me write down what I'm doing here. I'm taking this value and I'm swapping the sign and I'm multiplying it by 2. That gives us this number. And for the second one, we're just going to multiply it by 3. So I should be able to do that in my head as well, but I don't want to embarrass myself. So 571.6 times 3 is 1714.8, and that's a negative 1714.8 kilojoules per mole. So if everything adds up over here, which it should, if we do this right, then everything will add up over here. 6H2 cancels with 6H2, and that's all that cancels. That gives us 4NH3 gas plus 3O2 gas goes to 2N2 gas plus 6H2O liquid. So the delta H for this reaction is just going to be these two numbers added up. That equals negative 1530 kilojoules per mole. Okay? And that's really all there is to them. They do get a little more complicated, but just by adding more reactions for you to have to work with. Now, one of the nice things about Hess's law problems, unless the questioner is being particularly mean, is they only give you the information that you need to solve the problem. All right, so that's a little hint in how to solve it. But for now, I want to get to the next level of this discussion. It's still Hess's law, all right? But we're going to start looking at this in a way that might be able to save us some time. And that's to make use of the fact that, remember, delta H of reaction is just a general term. But if we take a look at these, I already told you some things like the delta H of fusion and the delta H of vaporization. If you take a look at this reaction here, methane. Look at reaction 3 here. Methane gas, 1 mole of methane gas being combusted to give carbon dioxide and water. So the combustion of 1 mole of methane. So that's the delta H of combustion. Remember what I told you, all these little subcategories. Delta H of vaporization is for 1 mole of H2O to go from the liquid to the gas. This would be the delta H of combustion. There's another kind of delta H that we're going to talk about. Look at equation 1. Equation 1 is taking carbon solid as you find it in nature. How do you know it's in nature? When you have a material that's a solid and it's not combined with something else, if just by itself in nature, when you find things by itself like this, that's usually how you find them in nature. So carbon solid, that's in nature. Oxygen gas, O2 gas, that's its most stablest form as you find it in nature. If you take elements in nature and combine them to give you 1 mole of something, that's what we call the delta H of formation, delta H sub F. We're going to now talk a little bit more detail about the delta H of formation and how we can use that as kind of a shortcut for Hess's law. So here's the heat of formation, delta H sub F. I mentioned to you the appendix in the textbook, and if you have the electronic form of the textbook, you can still get to the appendices. Very, very useful, especially for this chapter. There's a lot of thermodynamic information on a lot of materials in table 4 of appendix 4. Sorry, table 4.3 in appendix 4. We're only going to concern ourselves with the delta H of formation information. Notice that it's in kilojoules per mole. Now, the specific definition for delta H of formation is right here. As I mentioned, but now you've got it in writing. We're going to form 1 mole of a compound from the constituent elements as they're found in nature. Now, these also have a little 0 sign. This is called a naught, N-A-U-G-H-T. That means it's under standard conditions. Those standard conditions are arbitrarily defined. And this is just for your information. Our standard conditions here are going to be at a constant pressure of 1 atmosphere and a constant temperature of 25 degrees Celsius. Okay? So under those defined conditions, we can measure what the delta H of formation is for all sorts of products or compounds rather. Here, I just grabbed certain parts of, it's a very, very long table. It goes on for like several pages. So let's take a look at this. Let's look at the NH3. Okay. Oops, I circled the wrong one. I want NH3 in as a gas, as you find it as a gas, not an aqueous solution. Let's just write out what would the reaction be? How would we form NH3? What are the natural elements of NH3? Nitrogen and hydrogen. So we're going to have nitrogen. And how do we find nitrogen in nature? Gen and INE are found in nature diatomically. So N2 gas plus H2 gas will form NH3. But now we are restricted to define the molar ratio that gives us 1 mole. I'm going to put the 1 here. Remember, when there's a 1, you never put it. But for emphasis, I'm putting a 1 here. So now we're restricted. We have to use fractions for our coefficients. It's going to be 1/2 N2 and 3/2 O2. That's what we need to give us 1 mole. Now, the reason I have those other things circled, take a look, right? If we define the delta H of formation for 1 mole of NH3, that has a enthalpy value of negative 46.1 kilojoules per mole. But notice up above, in reaction 1, look at that value, negative 92.2. It's twice as much as the delta H of formation. For NH3, how many subscripts can I write in one term here? Okay, so that value is twice the delta H of formation for NH3, because just like with Hess's law, if we wanted to find that reaction as written, it's going to be the delta H of formation reaction multiplied by 2. Here, once again, we've got what looks like a formation. We're making H2O from its constituent elements as they're found in nature, hydrogen gas and oxygen gas. But that's not for 1 mole, that's for 2 moles. So if I take that value and cut it in half, so what's half of 571.6 negative? Well, let's take a look, because it should be what's right here, H2O liquid. It's going to be negative 285.8. That's the delta H of formation. We just needed twice that molar ratio, so we doubled the enthalpy component in the reaction above. All right, so let's write this one down as well. So to define the formation of 1 mole of H2O, it would be 1 mole of H2 gas plus 1/2 mole of O2 gas. That will form 1 mole of H2O liquid. Okay? So all we're doing here is calculating the delta H for 1 mole. Now, the other thing to point out on a table like this is for an element that it's already there as you would find it in nature. So if we wanted to look up the delta H of formation of O2 gas, by definition, it's already made, because we're making something from its constituent elements as found in nature, and that's how it is found in nature. So the delta H of formation for something as it's already found in nature is going to be 0. All right, and that's exactly what this little bullet point says right here. Okay, so that's the concept. Now let's do a Hess's law problem just using delta H of formation information. So I'll lead you through this one. Here's our balanced equation. It's the same task, except now notice that reaction 1 and reaction 2 are both delta H of formation reactions. So that's the information that we're given. This is no longer delta H of reaction, although it is delta H of reaction, but this particular reaction happens to be the delta H of formation for forming 1 mole, and it's under standard conditions. So if it's under standard conditions, all right, we can use the values in appendix 4.3. Here, I don't need to write an arrow for that. It says it right up on top. But the rest is just Hess's law. So now let's do it. How do we manipulate reaction 1 to give us what we want. So we've got nitrogen gas as a reactant. We need nitrogen gas as a product. And we've got ammonia. This is the same as what we did before, right? It's the same exercise. But now how we manipulate it is going to be a little bit different because we're working with a formation reaction. So we're going to take reaction 1, we're going to do it in reverse, but now we have to multiply it by what? By 4. All right, so let's do that. We're going to take number 1, we're going to run it in reverse, and now we're going to multiply it by 4. That's going to give us 4 NH3 gas goes to 2 N2 gas plus, let's see, 6, right? Because 4 times 3 is 12 divided by 2 is 6 H2 gas. And if we do that, the delta H of that reaction, now, of course, we already know what it's going to be because we did that. It's the same as above. See, we're just solving the same problem as we did here, except now we're doing it with formation reactions instead of what's given here. That's the only difference between these two problems. That's why I'm leading you through it. So the final delta H of reactions are going to be the same as above. Reaction 2, we're going to now multiply it by what? By 6. That's going to give us 6 H2 gas plus 3 O2 gas goes to 6 H2O liquid. Okay. We're doing the same thing. We're just now working with formation reactions specifically. And the reason I'm leading you through this is to show you that if we understand how this works, then we can actually take a shortcut. If we know that we're working with delta H of formation values, we can use this shortcut right here. And it looks crazy and complicated, but it's really, really simple. All this equation is saying is that we're taking the sum of the delta H of formation from the products, and from that we're going to subtract the sum of the delta H of the reactants. But this is basically just doing Hess's law. And let me show you. Right, so notice that what we're doing above is if we're dealing with a reactant, we're reversing the formation reaction. That's what we did for reversing reaction 1 because we needed NH3 as a reactant. But the definition of a formation reaction is that we're forming it. It's a product. So all the reactants are reversed. That's why there's a negative sign here. And we're just going to sum them up. Now we also need to apply what the molar quantities are for each reactant. So let me just lead you through it. So if I wanted to calculate the same delta H of reaction using this equation, I would start with the products, because the products, that's already a positive value. Delta H of formation, by definition, is whatever it is we're making, that's a product. 1 mole of it. Well, the delta H of formation is for 1 mole of it. How many moles of N2 do we have? We have 2 moles of N2 in our balanced equation. Sorry, I should point. You don't know what I'm pointing at. Let's look at the balanced equation up top. We need 2 moles of N2 as a product. The delta H of formation for 1 mole of N2 is going to be coming from reversing reaction 1. What did I tell you for things that are found in nature? What's the delta H of formation for N2? It's 0. So we have 2 moles, but the delta H of formation is 0. So this is for N2. So I'm going to put it in here so you can see everything. And we're going to add to that the component coming from the other product, which is H2O. We have 6 moles of H2O. That's H2O liquid. And we have the delta H of formation up there for H2O liquid. That's negative 285.8. All right, and that's everything. That's the products, the sum of the delta H of formation of the products. And then I'm going to subtract from that the sum of that from the reactants. So in the reactant side, I have 4 moles of ammonia. And the delta H of formation for ammonia is reaction 1. That's negative 46.1. But remember, that's for forming NH3. We want it as a reactant. That's why it's here after the negative sign, because the negative, right, that negative in the middle, that's going to reverse. This reverses everything. So this is going to be for the NH3. And then we need a term for the O2. We have 3 moles of O2. And what's the delta H of formation of the O2? 0.0, right? So now, math-wise, well, it's pretty easy. It's going to be 6 times negative 285.8. So that gives us, here, let's just put this in. This is going to be negative 14.8. Negative times a negative is a positive, plus 4 times 46.1, which is 184.4. And that gives us, surprise, surprise, 1530 kilojoules per mole. So this is a really good shortcut. And it's even better if you understand how it's working. I mean, your other alternative is to just memorize, oh, I know how to use this, and just what we say, plug and chug away, okay? But I think it's important to understand the tools that you're using and how it is that this equation works, all right? But it's all Hess's law. So let's see if I can wrap this into one more example here. Here's a combustion reaction. Here's some propane, C3H8. It's already balanced for you, okay? And let's just solve this using, here's a table of delta H of formation values. So for those of you who brought your calculators with you, why don't you try the plug and chug and at least make sure that mechanically you can solve a problem like this. So I'm going to jump in and just start solving this. I'm assuming that you've got the setup right. And if you don't have an answer yet, you're just trying to plug everything into your calculator. So let's use our equation. We're going to start with the products. We have, so delta H of reaction. That's going to be 3 moles of carbon dioxide. And the delta H of formation for carbon dioxide is here at negative 393.5 kilojoules per mole. And to that, we're going to add 4 moles of H2O. Now, in this case, it's H2O gas. So you need to make sure, especially if you're grabbing these numbers directly from Appendix 4, you have to make sure you're using the right value. In this case, you're given H2O gas for formation. The number is going to be a little bit different because, as I mentioned, they're going from gas to liquid, there's an enthalpy component there. And yeah, they do add up, right? If you took the delta H of fusion, you'll find that that difference will explain what you would look up for delta H of formation of H2O gas versus liquid. But that's a side comment. Right, let's add this number, minus 241.8. That's for the products. And then from that, we're going to subtract the reactants, which is 1 mole of propane. That has a delta H of formation of negative 103.8, plus 5 moles of oxygen, which is 0.0. And if you set that up correctly, that's the setup. Numerically, I got negative 2043.9 kilojoules per mole. That's supposed to be kilojoules per mole then. Okay, so that's the plug-in chart. But now let me tear this apart and show you again what this is doing with the formation reaction. Now we're not given the formation reactions, okay? But let's see if we can figure out what they might be. What would the formation reaction be for forming 1 mole of propane gas? What do you think it is? 3 moles of carbon, because 1 mole of propane has 3 moles of carbon in it, right? So if I took 3 moles of carbon as you find it in nature, and how many moles of hydrogen gas would I need? 4. 4 moles of H2 gas. That would be the formation reaction. For oxygen, we don't need it because it already exists that way in nature. How about carbon dioxide? You saw that one already. That was 1 mole of carbon as found in nature, plus 1 mole of oxygen gas as found in nature. Gives you the formation reaction for 1 mole of carbon dioxide. And H2O, you've seen that one before too. That's going to be 1 mole of H2 gas plus 1/2 mole of O2 gas. Gives you that. Okay, so let's call this reaction 1, and we'll call this reaction 2, and we'll call this reaction 3, and let's do this the old-fashioned way, so to speak, via Hess's law. Okay, I'm going to now manipulate those 3 thermochemical reactions to give us what we need. So let's look at the first one. We've got 1 mole of propane as a product, but we need 1 mole of propane as a reactant. So I'm going to take reaction 1 and run it in reverse. So my reaction 1 is 1 mole of C3H8 gas will now decompose into 3 moles of carbon solid plus 4 moles of H2 gas. And so all I did was reverse the reaction. So delta H of this reaction is going to be the reverse of what it was. So that's going to be positive 103.8 kilojoules per mole. Let's take reaction 2. We need 3 moles of carbon dioxide as a product. This is for 1 mole of carbon dioxide as a product. So I'm going to take reaction 2 and I'm going to multiply it by 3. That gives me 3 moles of carbon solid plus 3 moles of oxygen gas will make 3 moles of CO2 gas. So delta H of reaction, we're going to take what we're given there and multiply that by 3. That's going to be negative 393.5 times 3, negative 1180.5. Okay, one more to go. H2O. We need 4 H2O as a product, and we have 1 mole here as a product. So we're going to take reaction 3 and multiply it by 4. That'll give us 4 H2 gas plus 2 O2 gas will give us 4 moles of H2O gas. So the delta H for this new reaction as written will be whatever that is times 4, 241.8 times 4, that'll be negative 967.2 kilojoules per mole. So once again, if these add up, then these will add up. 3 carbon cancels with 3 carbon. 4 H2 cancels with 4 H2. That's it. So let's bring everything down. We've got 1 mole of C3H8 gas. On the reactant side, we have 2 plus 3 equals 5 moles of oxygen gas. And then on the product side, we've got 3 moles of CO2 gas and 4 moles of H2O gas. So that's exactly what we wanted, which means we did our Hess's law correctly. So you add these up over here, and you better get what we had up above, and of course we will. It'll be negative 2043.9 kilojoules per mole. And again, you can see then where all of these numbers and the coefficients and what we did with the manipulations, because look, here we took reaction 2 and we multiplied it by 3. Well, here it is, reaction 2 multiplied by 3. We took reaction 3 and multiplied it by 4. Here it is, reaction 3 multiplied by 4. And then we also took reaction 1 and flipped it. Well, here's reaction 1 flipped. Okay, it all works. Let's just start at the top. We don't have to necessarily do these in order. And I might not solve all of these for you, but at least show you the process involved in the solution. You had access to these, so maybe some of you already worked these out. So number 1 is determine the change in enthalpy for the following reaction from the enthalpies of formation. So that's delta H sub F for the reactants and products. And then I've given you some of the data from Appendix 4. And it's all listed for you there. So when you approach a problem like this, how do you want to solve it? What formula might you use? Or what process might you use? Where do you even start? Anyone have an idea? Yeah, go ahead. So write down everything that's given to you on the slide, right? That sometimes helps. Let's do that. So we've got delta, so this is all delta H of formation information, and we've got NH3, and we've got NO2, and we've got H2O. You could write all that down. I mean, or you can extract it from this, right? I don't want to say that everyone has to do it this way, but sometimes organizing is helpful. NO2 is plus 33.2. H2O is minus 285.8. Well, what kind of formula might you use, or what kind of process might you use with this? Is this a heating curve where we want to draw out the different components of the heating curve? Is it a Hess's law problem? Is it a coffee cup calorimetry problem? What kind? Here, let's do a show of hands. Number 1 is heating curve. Number 2 is coffee cup calorimeter. And number 3 is Hess's law. What do you think? Show of hands, 1, 2, or 3. What kind of problem is this? We've got 3, 3, 3. I see 3s and a lot of uncommitted. So, okay, so 3. Yes, this is a Hess's law. So when Hess's law, we've got 2 types of Hess's law problems. One is where you're given all this information, like this one. This is also a Hess's law problem. This one you can see a mile away. This is Hess's law. And you have to manipulate the reactions and total everything up. Right? But if you recognize this is a Hess's law, it's not all lined up like that. So how are you going to use Hess's law with this problem? Products minus reactants. So remember, this is delta H of formation. And that's the last thing that we did. When you have formation reactions, you can use those enthalpies of formation and do the sum of the products and then minus the sum of the reactants, and that will total up to give you what the delta H of the reaction is. Right, so that's that crazy looking problem equation with the sigmas in it that we did the last time. So let's just write out what the reaction, or sorry, what the equation is here that we're using it. We're going to calculate, we're asked to calculate delta H of formation, determine the change of enthalpy. So delta H of the reaction, sorry, that's what we're asked for. Delta H of the reaction is going to be equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Right? So that's challenge 1. Figure out what you need to do for the problem. Challenge 2 is to now take the values that you're given and plug them in appropriately. So now let's do that. Here's the balanced equation, and we have all the information written down. So we want to start with the products here. We've got 2 moles of NH3, and the delta H of formation for NH3 is negative 46.1 kilojoules per mole. So that's going to be 2 times negative 46.1. And then to that, we're going to add 4 moles of H2O. So 4 moles. H2O liquid is negative 285.8 kilojoules per mole. Okay, and that is all the products. And from that, we're going to subtract the sum of the delta H of formation from all the reactants. Well, that's going to be 2 moles of the NO2 gas. That each mole is plus 33.2 kilojoules. Whoops. And then we're going to add to that 7 moles of H2 gas, but H2 gas isn't given to us in our information, but H2, that's how you find it in nature. So it's 0. Okay, and that's the setup. The rest of it is just algebra. The rest here, I'll just challenge you to make sure that you can use your calculator the right way. When I did this back in my office, the answer I got was negative 1301.8 kilojoules per mole. Okay, and it's the shortcut that we take in Hess's law because we're using delta H of formation information. And I took you through all of that logic and the demonstration of why that logic works in the last lecture. So I'm not going to repeat that again. If you want to remind yourself of that, you can rewatch the lecture. All right, question 2 is really the same type of question as 1, except that there's a difference. Your unknown is in a different place. Now, with all of these computational problems, I don't want you to learn how to just plug and chug into the equation, which of course is what most students will be doing anyway. But if you know how to use the equation, then you should be able to solve any problem that uses that equation given any unknown. And that's not just for this class, for any class where you're using an equation, you should be able to know how to manipulate that equation so you can solve for any of those variables if they're unknown. In this case, the equation is the same. Delta H of reaction here. I'm just gonna copy and paste it here. We're starting with the same equation, but now the information is different. Now we're given delta H of the reaction. We don't have to solve it. All right. So you do need to read through a problem and make sure you know not only what tools you need to use, but what you're being asked to compute. Because a lot of times where students get messed up is they see a problem, they go, oh yeah, I know how to solve this. And I take the equation and you start solving it in a way that you don't need to because you're already given that information and you don't realize it and you get stuck. So you're already given delta H of reaction here. It's negative 197.8 kilojoules per mole. You're asked to determine the delta H of formation for SO2 gas. Where is that? That's right here. This is your unknown. So let's fill in the rest of the equation and see what we need to solve for. So this is going to be equal to the sum of the enthalpy of formations for the products, which is going to be 2 times SO3 gas. And SO3 gas, you're told right here, that's negative 395.7. Okay. So this is for SO3. And that's all we have in the products. For the reactants, it's going to be the 2 moles of the SO2 gas, but that's our unknown. So let's just call that X. This is for SO2. And to that, we're going to add 1 mole of O2, But again, O2, that's how you find it in nature. So this is 0.0. So algebraically, this still distills down to a pretty simple problem. All right, the challenge is figuring out how to set this up and solve for the correct unknown. So algebraically, now this just becomes negative 197.8 is equal to whatever this is, 2 times negative 395.7 minus 2x, and you solve for x. So once again, I'm not going to go through showing you that I know how to use my calculator. This is the setup. All right. When you do it properly, you do the math properly, you should get negative 296.8 kilojoules per mole. All right, I want to give you guys a chance to work some of these. So let's see. Let's do, and I'm not going to tell you what kind of question it is. Let's do number 6. I'm going to give you a minute or two to work on number 6. And feel free to consult with your neighbor. Okay. Right. Let's show you how we get that. Q equals the mass times the specific heat capacity times the change in the temperature. So Q is equal to the mass times the specific heat capacity times the change in temperature. Now, do we have all this information? Let's see. So we've got the mass, that's 10 grams. We have the specific heat capacity, which is 0.45 joules per gram degree Celsius. Now we don't have the delta T. We have the initial temperature, but we don't have the final temperature. All right, so some of you might get confused about, well, how am I going to solve for delta T? And you actually want the final temperature. So you might remember that delta T is equal to T final minus T initial. And you're told T initial is 25 degrees Celsius. Well, if TI is equal, well, I don't need to write that down. TI is 25 degrees Celsius. So we could say that T final is equal to delta T plus 25 degrees Celsius. But that's still 2 unknowns, right? We're trying to solve for T sub F, and we need to solve for delta T. But look at this, we can solve for delta T because we also know what Q is. Q, we're told that there's 9.5 joules of energy that are, in this case, being put into the system. Unlike in a coffee cup calorimeter, you're measuring the temperature of the water, right? Here, we're just following Q, and we're putting that energy into the system. So this is going to be equal to 9.5 joules. That's Q. Delta T, that's our unknown. So we can just solve for delta T and then add it to 25 degrees and we'll get our answer. So let's do that. So delta T is going to be equal to 9.5 joules divided by 10 grams times 0.45 joules. And now that's joules per gram degree Celsius, but that also means that those units, I'm going to put them now in the numerator, joules per gram degree Celsius, because it's really the inverse of the specific heat capacity now. And I'm doing it this way so you can see how the units cancel out, giving us the units of temperature in the numerator, which is what we want for delta T. And you do that, and I got, so I don't want to walk over there and get my calculator, 2.1 degrees Celsius. So that plus 25 gives us 27.1 degrees Celsius. That's our new final temperature. Okay, good. Let's see. Well, what kind of question is this? Number 5. We can do this one. In general, what are we doing? Heating curves, right? We're going from minus 20 degrees Celsius to 85 degrees Celsius. So for these, I always recommend draw yourself a little graph so you can keep track of what you're doing. We're going to start at minus 20 degrees, and this is H2O. So we know that in fact, you're told that the melting point is 0 degrees. So in case you didn't know, that's your melting point. So in our heating curve, as we add energy to the system, the temperature raises from -20 to 0. But then when we're at 0, the temperature doesn't rise as we're converting from the solid phase to the liquid phase. And once we're all in the liquid phase, we continue to add energy. Now the temperature is going to increase, and we're asked to take it up to 85 degrees Celsius. So we've got 3 components. Each component has its own enthalpy requirements. Section 1, we're going to take H2O that's all in the solid phase, and we're going to take it from -20 degrees to 0 degrees. The mass is 25 grams. So we have 25 grams of H2O. We know what the specific heat capacity of H2O in the solid phase is, but you've got to look that up in the textbook. It's 2.11 joules per gram degree Celsius. Grams cancel with grams, that's joules per degree Celsius. And we know the degree Celsius, T final minus T initial. So that's 0 minus -20. So this is going to be +20. And that's going to give you some answer in joules, right? And then section 2, now we're going to take H2O, and we're not changing the temperature. We're in that middle part of the curve. We're just converting from the solid phase to the liquid phase. So for there's no delta T because the temperature is not changing. But for that, we have the delta H of what that we're going to use? Delta H of, is it delta H of vapor, delta H of fusion, delta H of combustion, delta H of formation, or delta H of, I don't know, make something up, because that's the wrong answer. Okay, what is it? 1, 2, 3, 4, or 5? All right, let's just do 1, 2, 3, and 4. Show of hands. What value do you need here? Correct. Number 2 is what you need. Delta H of fusion. All right, fusion is going from the solid to the liquid, or from the liquid to the solid, depending on which direction you're going. That's going to affect the sign. All right. In this case, we're adding energy into the system. So the sign is going to be what? Positive or negative? It should be positive because we're adding energy to the system. This one is 6.01 kilojoules per mole. But we want to use a positive value here because we're going from the solid to the liquid. So that's going to be 25 grams of H2O, but we need it, this is per mole. So we need to get this into moles. That's 18.015 grams per mole. Now we use the delta H of fusion, which is 6.01 kilojoules per mole. And it's a positive value because we're going from solid to liquid. So that's going to give you a number in kilojoules. And then for phase 3, now we're all in the liquid phase. And we're going to raise the temperature by 85 degrees. So we've got 25 grams. Now we need the specific heat capacity of H2O, which is the 4.184 joules per gram degree Celsius. And the delta T, in this case, here we're going from 0 to 85. So T final 85 minus T initial 0 is positive 85. And you get some answer in joules. And then the last part, because we're asked to calculate the energy required to do all this, you just have to get everything into the same units, whether it's joules or kilojoules, and then add them up. So I'm not going to do that last step. I think you know how to do that. Okay, so that's the setup. I don't think we need to spend more time on that. All right, let's, I want to do number 4. This one is a little challenging in how to think about it and how to set it up. Once you have it set up properly, it's just a bunch of algebra. Okay. So we've got some AU. What does AU stand for? Gold. 20 grams of gold. There's the specific heat capacity of gold. And you're heating it up to 90 degrees Celsius, and you're placing it into a coffee cup calorimeter that has 20 grams of H2O. So you did an experiment just like this in lab last week. Okay. But here the math is a little bit different. You're asked, what's T final? T final of what? Does it matter if it's the final temperature of the metal or the water? It's both, because the final temperature will be the same for both because it came to thermal equilibrium. I don't want to flip back to the very first slide where I had the red square and the blue square, and you move them together, the heat transfers, but the transfer stops once both are at the same final temperature, because that's what thermal equilibrium is. So we just need the final temperature of the whole system. So to solve this, it's a little bit tricky. We're going to take advantage of this relationship. Q of the calorimeter is equal to minus Q of the reaction. And let's just tabulate everything that we've got going in here. All right, the calorimeter. Let's do that side. The calorimeter has got 20 grams of H2O. The specific heat capacity of H2O is 4.18 joules per gram degree Celsius. And the temperature change that was experienced by the calorimeter is some initial temperature, which was 26 degrees, minus the final. Sorry, final minus initial. So we want T final minus that initial temperature, 26 degrees Celsius. And if I knew what T final was, that would be delta T, and we can compute what the Q of the calorimeter is. Okay. And I'm going to set that equal to negative Q of the reaction. The reaction is we have 20 grams of gold. Is it 20 grams of water as well? It is. So it's 20 and 20. Okay. 20 grams of gold. Whoops. The specific heat capacity of gold, it's 0.129 joules per gram degree Celsius. And delta T. Now in this case, we don't know what the final temperature is, but we know what the initial temperature is. We heated it to 90 degrees. So T final minus T initial, which in this case is 90 degrees. Now, if you just notice what's going on here, we know that T final is going to be less than 90 degrees. So we know that this is going to be a negative value, but that's why there's a negative sign here. So overall, we're going to calculate some energy component on the right-hand side, and it's going to be equal to the same energy component that's on the left-hand side, because T final for the water is going to be higher than its initial. So this is a positive value, and everything else is positive on the left-hand side. And I'm going to leave it to this step, because the rest of it is just algebra. All right. And if you